Hello everyone. In this video, you will learn how to predict if you have an oxide or a peroxide ion in ionic compounds. So first, we need to know what is an oxide ion and what is a peroxide ion. Okay, so let's look here at the table. So here we have an oxide. An oxide is when we have oxygen with a -2 charge. A peroxide is when we have an O2 with -2 charge. Okay, so I will explain how to predict if you have an oxide or a peroxide ion with few examples. Okay, so let's talk about this one. So here we have manganese and we have oxygen. Okay, so let's write the name for this compound. So first, we notice that manganese is right here, is a transition metal, okay? And here is my oxygen, okay? So remember that transition metals, right, the charge of transition metals are not that predictable. And what that means is that they change, right? They can have one or more charges. And for example, here we have the most common ones, but it can be a different one that is not shown here. Okay. However, the elements in groups 1 and 2, they are very predictable. What I mean by that is that they always are going to be +1, and group 2, they are going to be +2 charge. Okay. The same thing for these elements around here. Okay. So that means they always are going to be always are going to be -1. All of these always are going to be -2, and here these are going to be always -3. Okay, so having that in mind, so how we can figure out the name for this compound and identify what type of oxygen do we have here. Okay, so this is going to be easy, but I want to show you what is the process. Okay, so here we have manganese and we have oxygen. So because we know that oxygen always is going to be -2, so I would like to start with that. Okay, this is -2. Okay, so here we can say, okay, so here we have a -2 charge from my oxygen. So that means that manganese have to be 2 plus. They have to be 2 plus because these charges, right, they need to cancel out, right? Because notice that here my formula have no charge, so these are canceling out. Okay, so that means that my manganese here is going to be +2. Okay, and in fact we know the table is indicating that manganese can be +2. Okay, so that means that we have what? This guy, right, is an oxide ion. Okay, so that was pretty easy, right? Because we only have one oxygen. Okay, so if we want to write the name, so that will be manganese 2, right? Because we need to specify the charge of manganese here in the name. Oxide, okay, manganese 2 oxide. Okay, So, but what about when we have two oxygens? Okay, so before to see other examples, there are few things that we need to understand. Okay, there are few things that we need to know, and one of them is that we need to have an idea. So, what is the structure of a peroxide? Okay, so a peroxide is when we have two oxygens bonded together. Okay, that's a peroxide, and each oxygen here is going to be bonded to something else, right? It's going to be bonded here, and also it's going to be bonded here with something else. Because we're talking in this case about ionic compounds, so that means that here we're going to have a metal, and also we are going to have metal on the other side to the other oxygen. Okay, so this is the general structure, right, of a peroxide. We're going to have two metals. I mean, these metals are the same, but we're going to have two, right, and two oxygen bonded together. Also, another structure for a peroxide, right, is having something like this. When we have the two oxygen together, right, because this is my peroxide, but instead of having two metals, we have only one. Okay, so this is another possibility. So we need to know this. Something else that we should know is that oxide are more stable than peroxide. And that is when both have the same metal. Okay, so that means if both have the same metal and we want to know which one is more stable, so the oxide are more stable. Okay, also we need to know that in most cases, ionic compounds having peroxide contain metals from group 1 and 2 on the periodic table. Okay, so we know we have transition metal peroxide, but those are not that common. Okay, and these are examples of those: zinc peroxide, mercury peroxide, and cadmium peroxide. Okay, so having this information in mind, let's see now other examples. Okay, so here we have manganese again, but now this time we have O2. Okay, so now it's a little bit different. Okay, so we have here our manganese, here we have oxygen, and here we have peroxide, right here on the table. Okay, so let's find out what do we have here. Okay, so let's see how we can do that. So we have manganese. Okay, so let's assume for a moment that we have an oxide, right? So that would be oxygen. Okay, let's assume for a moment that what we have here are oxygen, peroxide, from peroxide, okay, ions. So I'm going to write this in this way. So because we have two, so I'm going to write this way just to visualize that we actually have two oxygens, okay? And that means that in reality, because we have two of them, in reality what we have is a -4 charge, a -4, right? We have each one have two. So in total we have -4. So what is that telling us? Is that the charge of manganese have to be +4 for this charge to cancel out. Okay, so notice here on the table that the manganese +4 is not given, right? It's not shown here, but that is a possibility. So manganese also can be +4. Okay. Okay, so following this, right? So that is makes sense, right? So we cancel here this, we cancel here, we cancel here, right? So we cancel the charges. So that give me 0. So that is what is indicating here is that this, right, this O2 actually is coming from oxide ions. Okay. Okay, so this makes sense, right? So, but what about if we try the peroxide? Would that work? Okay, so let's see. So let's do exactly the same. So we have manganese here. And instead of using the oxide ions, so we're going to use now the peroxide ion. That will be O2 with a -2 charge, right? This is what we have over here. Okay. So in this case, so then we say, okay, so here we have a charge of -2. So that would mean that manganese should be a +2 because they need to cancel out and then give me 0. Okay. So what this means? So it looked that both cancel out. So it's looked that both look like they are the correct answer, right? But it cannot be both, right? So in this case, so this is a peroxide, right? Okay, so in both situations, it looked like they make sense, okay? But there's something that we need to take into consideration here. When we have this situation here that both look that make sense, right? That are possible. So we need to know, we need to remember that oxides are more stable than peroxide, right? When they have the same elements. Okay. So based on that information that we know, right? Because this, okay, so this is experimental observations, right? In experimental observation it has been found that oxides are more stable than peroxide, right? But this is of course when they have the same metal. Okay. Okay. So what is that is telling us that when we have a situation that both, right, satisfy the conditions, right, so that means that the most stable is the one that is going to be the more correct. So which one is most stable? The oxide is the most stable. Okay, so that's why it's not a peroxide. Okay, all right. So now we know why this O2 is coming from oxide ions. Okay. Now, how do we write the name? So the name is manganese 4, right? Because we find out that it has to be 4 for those charges just to cancel out, and oxide. Okay. So that manganese 4 oxide. By the way, if you're wondering how do I know this, because there are other tables that give you more information about the charges for these transition metals, and it has been found that manganese also can be +4, right? It can be even up to +7. Okay, okay, all right. So this is a good example. So let's see another one. Okay, so here we have strontium, okay, and O2. And again, we want to know if this O2 is an oxide or is a peroxide. Okay, so we know where is, let's find out what SR is, right? What is this a metal? Okay, so it's right here. It's in group number 2, okay? So that means that SR always is going to be +2, okay? Always is going to be +2. So is SR always is going to be +2, right? So that means that we have a charge of +2. The other species here, this species, that is my oxygen, it have to be -2, so they can cancel out, right? And the only one that can give me a -2 here is a peroxide group, a peroxide ion, right? Because it's the one that have the -2 charge. Right? So that means that this guy is actually coming from a peroxide. Peroxide ion. Okay, and here, so we have no other option, right? Because SR always is going to be +2. Excellent. Okay, so the name for this, that will be strontium peroxide. Okay, so let's see one more example and see how we can analyze this. Okay, so this is interesting, right? This is a little bit different. So here we have rubidium, right? And rubidium is in group 1. Okay, rubidium is in group 1. So that means that rubidium always is going to be +1. So then we can say, okay, so we have rubidium here, always is going to be +1. But we have two of them, right? So we have two. Okay, so let me just write here then again rubidium, right? So we have 2, so that means that we're going to have in total 2 plus charge, okay? So to cancel these two charge, the other species, the O2, have to be -2, right? So they can cancel out, okay? So that means that this O2 actually is a peroxide, okay? That makes sense. So this is 0, right? Because if you use, if you assume for a moment that you have an oxide, so an oxide is going to be different, right? Because it's going to be 2 oxygen, and each oxygen is going to have what? -2 charge, each one. In total, you're going to have 4, right? So -4, and here -2. So the charges will not cancel out. Okay, so that won't work. Okay, they need to cancel out, right? Okay, so we have no more option here, so that means that this guy is in fact a peroxide ion. Okay. So now we want to write the name. The name would be rubidium peroxide.